In the name of the Almighty, the Compassionate, the Merciful. Today we shall be speaking about the application of derivatives. In fact, in our previous lessons, all we did is to verify that, for example, a function is differentiable, etc. I mean, all we could do is to obtain the derivative of a function. Now we we speak about many applications. The application of derivatives. In fact, there are so many applications to the derivative, to the subject of differentiation, of which, for example, the how to calculate square roots. For example, if you wish to calculate the square root, for example, of 27.02, how would you do this? You do this, of course, using your calculator. But how does calculator achieve this? It actually accomplishes this using some kind of software built in, which uses methods like the calculus, etc. Another application, for example, if you wish to calculate limits that are more intricate than the ones we have encountered before. Like, for example, you wish to calculate the limit of when x tends to 0 of x ln x, for example. You put here 0 plus because ln x is verified for values of x greater than 0, for things like this. Also, the subject of optimization. Optimization, when, you, for example, they ask you, for example, try to construct a rectangle, this is trivial, of maximum area such that, for example, its perimeter is constant. All these kind of application, as well as others, all use the application of derivatives and differentiation, or they are what we call calculus applications. In fact, today we shall be speaking about many subjects. First, the mean value theorem, which is behind all kind of approximations of functions and Taylor formula, and then Maclaurin series, finite expansions, and then the theory of approximations. First of all, we start by the mean value theorem. The mean value theorem, it allows you to calculate the value of a function in terms of its value at another point, its value of a function at a point B, for example, in terms of its value at another point A, and with the remaining term that depends on the derivative at some point between the two. In fact, this theorem relies upon a lemma, or I would say a theorem, which is very important, called Rolle theorem. Rolle theorem tells you this. If f is continuous on a closed interval AB and differentiable on AB, and if f of A is equal to f of B, then there must exist at least one point in the open interval AB at which f prime of C is equal to 0. In other words, we can explain it like this. Suppose you have here a graph, and this graph is continuous and differentiable, and this function is differentiable in the open interval AB. And then you have, by chance, that f of A, the value of f of A here, is equal to f of B. Then you must have a point at which the derivative vanishes. Why? Because since you go up the mountain, and then you climb up, and then you go down, further down to the same point, then you must, logically, you must reach a point at which the derivative is equal to 0. Because if the derivative is not equal to 0, it means that f prime of C is either increasing all the time, so that you would not be able to come back to a value which is equal to the one that you started from. So in fact, there must be a point at which f prime of C is equal to 0. To apply this on an example like this one, this is a simple example. This is a polynomial. Polynomials are, in fact, functions which are continuous everywhere and differentiable everywhere. And if you take, for example, you check the value of f at 1 and 3, you would find that these 2 points, f at 1 is equal to f at 3, both are equal to -8. So the theorem tells you that there must exist a point at which f prime of C is equal to 0. How you get C? All you have to do is to differentiate, and you apply and you substitute by C. You set this equal to 0, which f prime equal to 0 according to the theorem, and then you find that C is equal to 2. So in fact, 2 lies between 1 and 3. So in fact, the theorem is correct. Of course, you don't need the example to verify the theorem, but just this is one simple example to show you how it works. Now, this Rolle theorem, although it's very simple, it actually led to another very important theorem called the mean value theorem. And this mean value theorem is, in fact, the theorem which is behind all sort of function approximations. If you wish to approximate a function, then you do some kind of, in fact, you relate the function at A in relation to another value at B. Like, for example, you wish to extract the square, the cubic root of 27.5. So you relate it to the cubic root of 27, which you know which is 3. So in fact, you do a kind of approximation, a value at A in relation to the other value at B. So it tells you this: if f is continuous on AB, the closed interval AB, and differentiable on the open interval AB, then there must exist a point, or more than one point, at which this point eta in the open interval AB satisfy this equation here, which is f of B is equal to f of A plus B minus A f dash at some point epsilon eta zeta between A and B. In fact, this you can prove easily. Suppose, for example, you construct a function of this sort: f of x is equal to f of x minus f of a minus f of b minus f of a divided by b minus a times x minus a. The function f is continuous on the closed interval AB and differentiable on the open interval AB. And here you realize something. For this function, capital function of x here, you realize that when you put x is equal to, you get what here? You get f of a minus f of a, and x is equal to, so you end up with 0, because this cancels out. While at b also, when you put x equal to b, you got here what? This cancels out with this one, and this becomes b, so in fact, again, it's equal to 0. So now you can apply a Rolle theorem. It tells you there is a function, capital F, which is continuous on AB and differentiable on AB, open interval as closed and open respectively, and it reaches two equal points, two equal values at A and B. So there must exist a point, zeta, for example, at which this derivative is 0. If you differentiate this, you get f of zeta. This is all constant, minus, and this is give you 1, minus f of b minus f of a at b minus a. And if you realize this, if you look well at this, you will find that actually this is another way of writing this expression here. The expression here tells you that f of b is equal to f of a plus b minus a f prime of zeta, and this is actually the same thing here. I'm sorry, this is prime. Here you write it just in a different way. In fact, it might be even worth saying here that this form could be more practical to use than the form that you have here. But still, it tells you what? It tells you that the difference of f, the difference between two values of f at a and b divided by the interval ab, it is equal to the derivative at some point lying between AB. It's like exactly, for example, suppose you take your car and you drive between two cities. Suppose, for example, we are in Egypt and you wish to do your journey start your journey from Cairo, and you end up in Alexandria, for example. The difference between the two cities as distance is 200 kilometers, and you accomplish this in 2 hours. So the theorem tells you that f of b minus f of a, which is the distance, here you have the distance and this is the time. So f of b minus f of a, which is the difference between in distance between the two cities, divided by the difference in time, or the time of the journey which it takes you, which is 2 hours. So in fact, you get 100. For example, you do it in 2 hours, so you have 100 kilometers per hour. So this 100 kilometers per hour is in fact your average velocity, your average speed during the journey. Of course, you don't travel at the speed of 100 kilometers all the time. You may rest at some other places. You may accelerate. You may decelerate. But on the average, your average speed is 100 kilometers per hour, which is equal to the distance 200 kilometers divided by 2 hours. To this end, actually, there is nothing new about it. All you have to do distance divided by time. But the theorem tells you something important. It tells you that there must exist a point, or more than one point, at which the speed must be equal to 100 kilometers per hour. In other words, at some point in your journey, your speed must reach 100 kilometers per hour, or at 2 points. Otherwise, because if you travel at a speed higher than 100 kilometers per hour, then surely you should arrive to Alexandria in a less than 2 hours. And same thing when you travel in a speed which is smaller than 100 kilometers, the journey takes more than 2 hours, etc. Actually, to exemplify this on using the applet of Bassem. This is the applet of Bassem. These applets, we told you before that they have been designed at the Faculty of Engineering of Cairo University by a young man called Bassem Ibrahim. And this young man, I asked him to give us some applets, to show us some applets in order to clarify this concept of calculus. So actually here he assumed he took any function here, and then he started, for example, by this point, 2 points. This is A and this is B. And the theorem tells you that there must exist a point between A and B such that the slope of this line, look here, the slope of this line, which is the angle of inclination of this line to the x-axis, or if you calculate the tangent, this is called the slope, it must be equal to the derivative at some point between A and B. And that's it, because the function is continuous and differentiable. So this is the point zeta at which it has the same derivative as the slope of this secant here. Both have the same slope. Of course, you may have 2 points, not 1 point, at which your speed becomes equal to 100 kilometers per hour. Like, for example, you wish, for example, to take a point, this point here, for example, and that point here. And you apply the mean value theorem. And you end up here, in fact, with 2 points, eta 1 and eta 2, zeta 1 and zeta 2. Those are 2 points at which your derivative, again, is equal to 100 kilometers per hour, etc. So actually, this theorem, it gives you an average value, and it tells you that there must exist a point at which you reach that average value. Now we go back to our theorem. Now you can actually take an example, the same example like before. This is the interval 1, 2, and you calculated f at 1 is equal to -8 and f at 2 -3. You subtract both, and you say that it must exist a point zeta between 1 and 2 such that your f prime is equal to the difference of these two values divided by 1, which is the difference between B and A. So here, f of 2 is equal to f of 1. This is the theorem. Plus 2 minus 1 f of zeta, from which actually f of prime of zeta is equal to -5. Does it exist as zeta such that in the interval 1 and 2, such that the f prime is equal to -5? Indeed, if you solve this equation, this is the derivative, you got eta 1.5, and 1.5 in fact lies between 1 and 2. Again, this mean value theorem can lead to a more elaborate way of approximating functions. This is not the only one. This is only it furnish the basis for example, at Taylor. Taylor actually, he is the scientist who lived at the time of Newton, and he was able, he as well as Maclaurin, to extend the mean value theorem by adding more terms. Taylor reached the following. He said that if f together with his n derivatives are continuous on AB and differentiable n plus 1 times on AB, then the expansion takes the following form. This form, in fact, if you wait here, if you cut it, if you truncate the series here, all you have to do is to add zeta here. You get the mean value theorem. And of course, you can of course also truncate here. So if you don't truncate, then it goes forward until, for example, you have n terms, and there remains a term which we call the remainder term, and this remainder term can tend to 0 and n tends to infinity for the convergence of such series. And this is a polynomial. In fact, the one in the preceding slide, this is a polynomial, n degree of polynomial, but of n plus 1 terms. So you have n plus 1 terms of n degree, and then there remain a term which we call the rest, and these terms actually give you the error between f of x and p of x. So you have a p of x. This is in fact what you have. You have a function p of x, and approximated by a polynomial n of x plus a remainder of x, and this remainder actually after n, this remainder after n terms gives you the error between f and p. So all you have to do, you need to say that you approximate locally your function by a polynomial of degree n, and that's the idea behind Taylor. So that's the expansion. In fact, it takes this form. F of x, like we said, is equal to f of p is equal to f of p plus is equal to f p of n of x plus Rn of x. And this is the remainder, as we said, and this is the polynomial which approximates f of p. For example, you have here a Taylor polynomial, or you wish to calculate Taylor polynomial of order 4 of sine x around p by 2. So you start by you start by writing the series. You have f sine x, which is f of x equal to f of pi by 2 plus x minus pi by 2 f prime of pi by 2, etc. This is the way you write your polynomial, and you end up with a series like this. This series, in fact, which is a fourth order polynomial, y is equal p 4 of x. This is contains 5 terms, and this is approximation to the sine x. This is the sine. The green curve here is your sine x, and blue is your polynomial which approximates this sine x. You see very well here that around the point pi by 2, that they are almost identical, and then they differ a little bit. Of course, the more you get away from the point pi by 2, the more your error increases. But in fact, the more you take some more terms, the more the error decreases or diminishes until it vanishes completely when you get to take the whole series. Here is f double prime, f3 primes, f4 at the point pi by 2, and then you write down your series. P4 of x is equal to what? Is equal to f of pi by 2, which is sine pi by 2 is equal to 1, plus x minus pi by 2 times the derivative of sine at the point pi by 2. Derivative of sine is cosine. Cosine pi by 2 is 0. So there is no term in x minus pi by 2. But then again, when you differentiate it twice, you get sine again at pi by 2 is equal to 1, etc. So you have a series of this expression of this form. This is a fourth order polynomial plus, of course, a remainder. And this remainders tell you that there is a little bit of difference between both terms, the f of x and the p4 of x. Of course, they coincide. Of course, if suppose the polynomial is f of x is a polynomial of degree 4, then you end up here and there is no error. But if this is a kind of transcendental function of sine e to the exponential function, etc., so there is some kind of discrepancy between your polynomial which approximate your function, and there remains some error which you can control it. Actually, if you wish to show this, this is again the apples of Assem. Here, suppose we wish, for example, to take, this is our point. Suppose we wish to take another point here, and then we increase the number of terms. This is a polynomial of degree 1. It tells you here that this is the degree of the polynomial, and since it's of degree 1, then you have 2 terms. If you have 2 terms, that it is a straight line. If you increase the number of terms, you get a parabola, and this parabola, in fact, it's better approximation to the curve sine x at the point, at this particular point. Like, for example, this point is, for example, 100 pi by 2 plus pi by 4, for example, like 3 pi by 4, etc. And you keep doing this, and you keep increasing the number of terms. The more you take the number of terms, the more you get a better approximation. Look, why? Because they both tend to each other, and the remainder tend to 0, because you are actually taking the whole series. Of course, we can take any other point. It's not necessarily this point. And the same happens again. Suppose, for example, you take another point here, and then you keep increasing the term to a parabola, and then third degree polynomial. And again, the more you take terms, the more you get a better approximation of your function, which is sine x, around the point that you wish to locally approximate or expand your function in terms of polynomials. Suppose you take another function, like, for example, the logarithm. We know very well that the logarithm exists only for values of x greater than 0. And, for example, you take, for example, a point like this point, and you increase again the number of terms. So you get a better approximation. But again, you end up with a point here that it never converges. Look at the point here. It never, they never get to one to the other. I mean, they never coincide. It keeps, even if you take more number of terms, the same happens, that you don't converge y. There is a reason for that, because you know very well that logarithm of x is equal to the integral of 1 over x dx. So if you, for example, you write it in this way, so you get 1 over a times 1 plus x minus a divided by a. And you, of course, you know very well that the expansion of this series, this is a binomial expansion of order when you get it into the numerator minus 1. So finally you get something like 1 minus x minus a divided by a minus x minus a squared divided by a all square, etc. Plus, I'm sorry, here, etc. And we know very much that the convergence of this series depends on, which is actually this is the expansion of the logarithm. It's a binomial and for negative powers. So actually it converges for each term here, the mod x less than 1. But here you have x minus a divided by a. So in fact you have some kind of convergence criterion. In other words, you have x minus a less than a, and because here a is positive, in other words, x must be less than 2a. So actually this is the convergence criterion, and this convergence criterion, in fact, this convergence criterion tells you that you are away from the point at which you cannot, in fact, you cannot approximate by a polynomial, and this polynomial is not would not converge because your point which you wish to calculate the value of x is away from the point at which you expand the function by distance which is not this x should be less than twice this distance. In other words, it keeps converging here, and then it entangles, it widens when x is greater than 2a. Of course, when you take another point here, then there is no problem. Why? Because this point, so long as for all values of x here are less than 2a, the expansion is all right. So in fact, when you they all they converge. In other words, they all are the error becomes small because the value of x corresponding to twice of this value here is away and is outside the monitor. So we go back to our now slides. Here you have the same formula of Taylor. It's called Maclaurin. The only difference is that instead of expanding around a point A, you expand around another point called 0. Why it's called under a different name, just because the proof was different, but it's the same thing. And if you wish to calculate Maclaurin series for different values for different functions, it is well known that, for example, this is the binomial. It goes this way with the if k is integer, a natural number, then there is no problem. If k is fractional or negative, then you must have a convergence criterion like mod x less than 1, and you keep going this way. This is the expansion of the exponential. This is the logarithm, and this is the expansion of the sine. Sine minus 1, cosine, etc. All these are the expansion of functions, and you found them in a book. Suppose, for example, you wish to calculate a Maclaurin series for this function. Would you go and use Maclaurin series and differentiate some? No, there is no point for doing this. Why? Because you know very well that the expansion of a square root of x, x1 plus x, is equal to what? 1 plus x to the power half. So it's equal to 1 plus half x plus half times half minus 1. Divided by 2 1 x squared. So in fact, if you have, suppose you have then 1 plus y to the power 1 half. So it tells you that it's equal to 1 plus half y plus you get now 1 minus here minus 1 over 8 y squared, etc. And all you have to do is substitute y is equal to x squared. And this is, of course, much simpler than doing the differentiation again. And because you know very well the binomial for k for the power equal to half, and we saw this before in a previous slide. So all you have to do, you get the expansion for the square root of 1 plus y, and then you substitute y is equal to x squared. And of course, the criteria of convergence are the same. Same thing when you have, for example, a logarithm, such logarithm, and you wish to expand the Maclaurin series. All you do is that the logarithm of the square root is equal to half the logarithm of the value here. The logarithm of 1 plus x over 1 minus x to the power half is equal to half this logarithm here. So in fact, if you know the logarithm, the expansion of logarithm 1 plus x, which is of this sort, and we saw it in a previous slide, these are common things that are encountered, you find in books, and you know the logarithm of 1 minus x, all you have to do to express the logarithm, this simple algebra, since this is equal to this, and you know the expansion now of ln 1 plus x and ln 1 minus x, all you have to do is subtract them one from another to obtain this formula here for the Maclaurin expansion of this function here. In fact, we wish to say something here, that these expansion of Taylor and Maclaurin are not the only ones. I mean, these fall into the category of what we call finite expansion. The meaning of finite expansion is that you wish to expand f of x in the form of a polynomial of x, again, with a term which defines the discrepancy between the two. This term, there is a person called Landau who said that you can write this in the form of x minus a to the power n. This is O Landau. This is a Landau symbol. And this is equal to x minus a to the power of n times epsilon of x, and this function actually tends to 0 when x tends to a. And this way of approximating functions actually may be more general than Taylor, but it doesn't matter. The idea is the same. The idea is you want to approximate a function locally around the point A by a polynomial of degree n. That's the idea. The idea is you want to approximate a function f of x, expand it locally around the point A by a polynomial of degree n, and there remained a term here which you can account for, and it tends to 0 as n goes to infinity around the point A. So in fact, suppose for example you have e to the x, you can write it this way: 1. This is Taylor expansion, or the Maclaurin around x equal to 0. Etc. And you keep going like this over factorial n plus x to the n plus 1 over factorial n plus 1. Of course, you have here a term of zeta. This is the remainder term, and you wish here to represent this term. Now, this term is what? Is O of x, because you have a is equal to 0 to the power n. In other words, is equal to what? To x the power n times x divided by n plus 1 factorial. This is factorial. And actually, this is epsilon here, tends to 0 when x tends to 0. This is epsilon. This is epsilon. So this tends to 0 when x tends to 0. So in fact, what you do is that you said that f of x is in the form of a polynomial of degree n, and the remainder a term which in fact which can be of this form. And this polynomial, in fact, is the best approximation you can get for this around the point x equal to 0, and this term actually can vanish. Now, in fact, this representation of Landau, or the what you call finite expansion, could be better sometimes than the expansion of Taylor. For example, if you have a function like this, for example, this function, in fact, we saw it before. We said that this function is differentiable at x equals 0 once, and it's not differentiable twice. Since the f is called have a finite expansion in the neighborhood of a point, if there exist real numbers a0, a1, a2, you can represent this function in this form: 0 plus x times 0, this is a1, plus x again squared times 0, plus an element of x squared, O of x squared. Why? Because you can get it, you can write it this way, times x times sine of 1 over x squared. Now you see here that this term tends to 0. How? By the squith theorem. The sandwich theorem tells you that since this is bounded, so this is tends to 0. And then you have, in fact, you have an element of O of x squared. Yet if you do this using your Taylor expansion, since it is equal to 0 plus x times the derivative at 0, which is 0, plus You cannot proceed further. Why? Because it is differentiable once and not twice. So you have a term here of eta, and then what you actually reach is that you have an O of x only, not of x squared. So in fact, your interest is not to expand in this way or that. Your interest lies in approximating your function by a polynomial. So the more you get a better degree polynomial to approximate that function locally, then you say that you have a kind of expansion around the point. And of course, the Taylor or Maclaurin are not the only ones. You have Taylor and Young, the form of Taylor and Young. You have also Lagrange form of remainder, etc. So these are not actually the only ones. Now the idea, of course, of the Taylor expansion and Maclaurin can lead you to what we call approximation. You can approximate a function like sine x. Students know that sine x for small values of x can be approximated by x when x tends to 0. Or for example, 1 minus cosine x approximated by x squared over 2. Or for example, e to the x minus 1 approximated by in the neighborhood of the 0 by x. All these kind of approximations tells you that for small values of x, you can approximate a function. So actually, from, for example, for this function sine x, this is the Taylor expansion, this is the remainder, the second is 0. So in fact, here, sine x is equal to x plus a remainder. So actually, this remainder here, you know very well that since cosine eta is bounded, so this remainder is less than x cubed divided by 3. And you see from the graph here, this is the green one, this is a sine, and the blue one is the function y is equal to x, the straight line, and you see that they coincide around the origin. Why? Because actually, Maclaurin expansion tells you this, that sine x is equal to x plus a term of x squared, which vanishes, plus x cubed, and this actually, this is the rest. This is the difference or the error between sine x and x in the neighborhood of the origin. So in fact, if you wish to calculate the error becomes of the form, because cosine eta is zeta is bounded, of the form of x cubed divided by factorial 3. So suppose x is small. Suppose you wish to know the difference or the error at in the neighborhood of the origin for values of x less than pi over 18. Would this be great? If you calculate this, you find that you substitute x here, and you find that the difference only is within the value of 9 times 10 to the minus 4. In other words, it's very negligible. Again, for example, suppose you wish to calculate an approximate value for the Euler number E. What you do is that you use the function e to the power x, and you substitute x is equal to 1, and this gives you the value of E. So what you do is that actually you use a series of representation, which is could be very well the Maclaurin expansion of e to the power x, and you keep calculate this series for values of x is equal to 1. Of course, you can take a partial sum, first term, second term, third term, etc. And you keep noticing here that these are the first approximation. This is the when you take one term, this is 2 terms, 3 terms of the series, and and this is the function, for example, e to the power x. So actually, you end up with what? You end up the more you take more terms, the more you take terms. This is actually the series, and this is known, and we saw it in the table before. So if you take only one term, you get 1. But if you take 2 terms and you substitute x is equal to 1, you get 2. So actually, this is the better approximation, and you keep doing that. This is the first. This is the if you take 3 terms, you get 2.5. So you see, in fact, that you go very quickly in approximating the value of E to 2.718. In fact, these are not the only applications of calculus. There are so many other applications. For example, suppose, for example, you wish to calculate the square root of 32. You know that 32 is equal, for example, to 36 minus 4. So you get this out. So you end up with 1 over 9 to the power 1/2. This is equal to what? 6 times 1 minus 1 over 18 plus half times half minus 1 divided by 2, 1 over 9 square, etc. And still you have other terms to go for. So in fact, this becomes equal to 6 minus third minus, for example, 6 times 1 over 8 times 81, etc. For example, if you calculate this, you will find, for example, 5.6 something. If you square this, you will find equal to 32 point, for example, 00, etc. So which means actually this is a good approximation to a square root of 32. This is one of the application of calculus. Again, there are some inequalities as well. Suppose, for example, they tell you calculate, for example, the limit of 1 minus cosine x divided by x square. We saw that if this is equal to x only, then you get 0. But suppose this goes to 0. And the limit, you can, of course, here you also use Maclaurin expansion of 1 minus x squared divided by square root of 2 plus etc. divided by x squared. If you take the limit here, this cancel out with this, you get 1 over 2. For example, again, suppose for the mean value theorem, they wish to ask you to prove that sine b minus sine a is less than b minus a, for example, or that tan b minus tan a is greater than b minus a. All these kind of inequality relies upon the mean value theorem. Because here sine b minus a, according to the mean value theorem, is equal to what? Is equal to b minus a times the derivative of this cosine at some particular point eta. But you know that eta is bound, cosine eta is bounded between -1 and 1. So this is less than 1. So you end up with what? With this inequality. Whereas for tan b minus tan a is equal to what? It's equal to b minus a. Is equal to b minus a times the derivative of tan, which is equal to sec square zeta, for example, a point between a and b. But the sec, you know that it is greater than 1. So in fact, since this is greater than 1 and this is equal to this, so in fact you end up that tan b minus a in modulus is greater than b minus a, etc. In other words, there are so many applications to derivatives. We just run out of time and we have to stop somewhere. But in books, you will find, for example, the application of derivative. For example, if you wish to calculate a higher derivative, like for example, you are given a function which is complicated, and they ask you to calculate the 7th derivative. You do a Maclaurin expansion, and then you locate the term, and you equate both expansions to obtain your derivative, etc. With this, actually, we come to the end of the lecture, and we spoke about the application of derivative. We displayed the mean value theorem, and then as well we talked about the general form, which is Taylor as well as Maclaurin, and we said that these kind of expansions lie in a greater world of expansion called finite expansions. And these finite expansions, the idea or the philosophy is to approximate or to expand a function locally by around a point, locally by a polynomial of degree n. And there remains a remainder which you can bound it so that you can approximate both. And finally, we spoke about the theory of approximation. And approximation, this is actually whether Taylor or Maclaurin, or whether the mean value theorem, which is even more used. It tells you, it gives you ways, it furnish ways in order to approximate functions, like for example the one that you saw. At the end, I wish to thank you for your attention, and I wish to remind you again that this lesson, together with the previous one, as well as the one that you're going to come later, all these are uploaded to the site of the MedNet-U, which is organized and administered by the Consortium Nettuno for distance learning, hoping to serve all the Mediterranean area. And again, all these applets that we showed here are the courtesy of the University of Cairo. They are done by a young man who are able actually to help me to provide some clarifications of the concept of calculus. And until actually we meet for another application of the calculus, I thank you very much for your attention. And until we meet, good luck and thank you very much.